It's working? So, good morning. Welcome to everyone. I guess that pretty much all of you already know me. I am Alessandro Chini, the coordinator of the Motor Vehicle University of Emilia-Romagna Master Degree in Advanced Automotive Electronics Engineering. And I'm very glad of introducing today's meeting, where basically we're going to see the presentation from our students of their project developed during the automotive electronic course. This course, which is held during the first semester of the second year, is a course where our students are challenged in designing a project, an electronic circuit proposed by Ferrari Motorsport, in particular by engineer Claudio Silenzi, and with the advice of Claudio and Professor Paolo Pavan, they go through the definition of the project and its realization. So this is something that happens pretty much every year. I mean, every year there is this constant contest of the project presentation. This time we decided to give it a bit of a better presentation, okay? So that's pretty much it, I think, Paolo. I don't know if there is more that I want to say. Just good luck to all of you, and I'm going to leave the stage to Professor Paolo Pavan that will continue. Good luck.
Thank you, Alessandro. So just practical things to do, logistics in some way. So you will have 30 minutes for your presentation. You should during the presentation, you should talk about the technical results you had, but also the organization of the work you did. So it's important that you speak about the organization of the teamwork. Two things. You will need to upload on the team section that you have for your group all the material. You need to put the documents, the final documents of everything. And you will receive, not all of you have received, so I will resend it. I will try to resend the messages. 2 evaluation forms, one for each other group. All right, so each one of you should follow also the presentation of the others and be ready to fill in the form, simple forms that are needed, because you are the real, the project is the same for all of you, right? So you know the details, you know the strengths and weaknesses, you will recognize the strengths and the weaknesses of the others' projects as well. Do not be too picky, because they will be picky with you as well. So try to be fair. Fair is enough, I think. It's a first time that you probably have this kind of thing in your program, and it's probably the only one. But it's interesting to see how different groups of students solve the same projects with different ideas and different propositions for. So Claudio, you know him already. He will talk about the technical part of the project that he decided. So as Leonardo is here as well from Ferrari, just for you, Leonardo, with Claudio we do it every year. Every year he chooses a new topic, and every year there is a new contest. And we have refined the procedure year by year, adding some meetings during the development of the project, just to make sure that there is this kind of feedback between the technical staff and the students, not to let them go, and drift somewhere else instead of being focused on the project. So Claudio has been very kind and helpful in this course for all these years, and I hope he will keep doing it forever in some way. And I think that from what I know, it's something that is really stimulating also for Ferrari, because they see different approaches. They can have some new and fresh idea, in any case, that can be proposed from students to them. So, and I know that when you will get some contact, and you will have for sure some contact with Ferrari, you will know how to handle that. It's important to know to show that you are able to organize the teamwork. So the so-called soft skills are something that companies are really willing to see. So in this case, you know already how to handle the group, how to manage the work, how to split the work in work packages, how to handle the timelines of all this and the scheduling of all the things. So I think it's going to be, I hope you enjoyed it. I know it's tough because you do not have any other chance than this one to do this exam instead of doing the exam many, many times. There is no way. You do it once in a lifetime and that's it. So it's important to relax and enjoy the presentation. You will need to show your capabilities. I'm sure it's going to be fine. I mean, it's always been fine. It's always been good. You are good students. You are really, I think, very motivated. And the results, we have been seeing good results in the past all the time. So I'm sure that this time will be the same. Just relax, enjoy, and give the best you can with your presentation. All right? Good. You will receive email, and please remember to upload your documents in the team section that you have. Please, Claudia, if you want to say something.
Good morning. Welcome to everybody. I'm happy to stay here for third year, I think, in a row. So as I said in last occasion we met, as Ferrari, for us the MUNER project is very important because it brings together the industry world with students, and it's important because students for the first time understand that the industry reality is less ideal than what they think, that the work that the industry requires to the people that works there is not ideal. Typically the requests are very trivial, without specification. And so every year we want to make that students understand how can they work in the future in industry. And so the project that we think for this project, for this exam, is very similar to the one that we typically faced in industry, in Ferrari. And the students that attended this course in past years thought that this was very useful for them. And the guys that was lucky to join Ferrari performed very, very well, also starting from what they learned from this course. So the soft skill that Paolo said before is basic, because we expect that students, that people that join Ferrari as a technical base that is fundamental to complete the job, but also the soft skills, so the capacity to work in team, the capacity to say I'm wrong, the capacity to understand problems, to solve problems, to keep calm, to look at timings, to make teams. That for us is very important. So I hope this course could be helpful for you in this respect. Good luck. Okay.
Can you, okay. Okay, good morning and welcome to everybody. I am Simone Cattin, the responsible for project management of the Group A. Here there are my teammates, in particular Michele Abruzzese, responsible for software design, Carola Buzzi and Nalanda Yoshi, responsible for hardware design, Enrico De Vincenzi, responsible for hardware test, and Matteo Totaro, responsible for software test. Let's see now how we have organized and planned these months of work. Well, we have faced many obstacles during these months in order to work at this project, because we had many strong deadlines to respect, such as the deadlines of today. And in order to minimize the waste of time, we need to decide who had to do what, based both on the hard and soft skill of each one. Because it has been a multidisciplinary project which goes from the organization to the hardware design, to the software design, to the testing, and to the writing of the documentation. So there were many things to do, and we based on the hard and soft skill of each member in order to choose all the roles. We keep ourselves in communication week by week in order to know the state of each task and in order to plan the task and to prioritize the task for the following week. And based on this consideration, we evaluate 5 parameters. In particular, the team size. We are only 6, so there was no need of strong delegation. We evaluate the flexibility, which was pretty much high. Apart from the last week of testing, we can develop our work basically from everywhere. The deadlines, as I said, were very strong. The deadline of today has been fixed at the end of September, so there was no way to delay it. We had also more or less fixed budget, because we could not make an infinite amount of attempts of doing this work. And we also had a collaboration with one of our stakeholders. So with Ferrari, we make 3 intermediate meetings in which we take some important tips in order to develop our work. Evaluating these parameters, we have studied 3 project management methodologies: Waterfall, Agile, and Kanban methodology. We didn't choose Waterfall methodology because it requires a whole knowledge of all the requirements before starting our work, so it was not our case. It was pretty much good, the Kanban methodology, but we have not chosen it because for our point of view, our project was too complex for this methodology, and was made up of different layers of work, so it was not good for us. So we have chosen an Agile methodology, which permits us to change our work, which permits us also to involve the stakeholder, as I just said, and also we have chosen this because we had no clear idea of how the final work would have looked like at the beginning of the project. Here there is a quick overview of how we have divided this month. Well, basically we have chosen to split it into 11 weeks, and these 11 weeks in 3 macro periods. We assign at each macro period an important goal. For example, in the first 4 weeks, we dedicated ourselves to the components research in order to deliver the full BOM at the end of October. Then from the week 5 to the week 8, we complete the hardware and software design in order to deliver the full PCB. And in the last 3 weeks, we performed the hardware and software test in order to have the final result that we are presenting here today. On the left, we can see also a restricted version of the Gantt diagram that we have developed and we have sent on Teams, which shows week by week which of the main tasks we have developed, such, for example, the project initialization, design, and so on. It describes week by week what we have done. Here there is a quick overview of the costs that we have sustained. In particular, we have chosen to distinguish among the effective cost, which is the real amount of money that we have spent, and the subtotal, because it differs for the other components on the right, because we had the possibility to borrow the connectors, the STM and the transceiver, for example. But if in the future someone wants to emulate our project, must take into consideration also these costs. And so we have reported also the subtotal, which includes also the cost for stock, because there are some components that has been bought but has not been used at the end of the work. Here there is a general overview of what we have done, starting from the tab in which there are the requirements given by Ferrari to us. We have chosen the CAN as the communication line, and then there is a very general scheme of the work that we have performed. We had the primary board, which communicates through sensors with an MCU, which transmits parameters through a secondary board to another MCU, and through the user protocol communicates to a terminal. Now I'll give the word to Carola Buzzi, the responsible for hardware design.
Good morning to everyone. Now we move to the hardware part. This is just the main layout of the PCB, just to show you the main component we will go through in the next slides. We start with the protection circuits in output. We have TVS diodes both for electrostatic discharge and for inverse current battery protection. We have PTC both in input and in output. We have some circuitry regarding current, voltage, and temperature measurement that my teammate Enrico will explain after. And then we move to the main component. We select a DC-DC controller, LT3840, which is a high voltage synchronous step-down controller capable of working from 2.5 up to 60 volt. And then we will move, let's say in the next slide, we will have some more deeply explanation about the input-output capacitor, the inductors, and the resistive divider. As I said, we start with the resistive divider. Why? Because it's the main responsible for the output voltage. Through the equation that is shown here in red, we can see that we have a dependence on the resistor in output. So we start by fixing R10, and through multiple simulation, we try to achieve the expected output voltage. Since there was no particular constraints in the datasheet, we obtained the output voltage by simulating with different value, trying to obtain the best ratio between R7 and R10. As it is shown, we achieved the 13.6 voltage, and in output, of course, depends on the load that we attach, and we obtain the 7.4 ampere for the output current. For what concerns the inductor selection, we took into account the minimum inductance value and the saturation current. We started by sizing the output ripple current, ripple current in the inductor according to the datasheet in the range, so 0.3 times the output current. Starting from that, we calculated the minimum inductance value. Since what we obtained was a fairly large inductor, what we did was placing two inductors in series. In the choice of those inductors, we took into account the saturation current as one of the main characteristics, because as it is shown here in red, we have a high transient spikes. So our inductor were able to sustain this high level current. Another important feature of the inductor that we select was good capabilities, good features in terms of saturation and inductance that were stable over temperature. And since, of course, the inductor are a critical device and very important, we took into account. For what concerns the input capacitor, of course, they say input capacitor are important to avoid both conducted and radiated emission to propagate into the circuit. So we use input capacitor to short high-frequency component to avoid pulsating ripple current to propagate into the circuit. In this case, we started by selecting, let's say, since, of course, exceeding the ripple current can degrade the performance and also the lifetime of the capacitor, we select a capacitor that had a maximum ripple current higher than the calculated one, according to the datasheet. And then to achieve the bulk capacitance that we calculate through the equation, we place two capacitors in parallel at the input of the circuit. For what concerns instead the output capacitor, the design was based on the output ripple voltage that we would achieve. So by substituting the output ripple voltage to calculate the equivalent series resistance, we obtain a fairly large output capacitance. So at this point, we had three main possibilities. One was going back to the design of the inductor, but this meant increasing the inductance and also the dimension of the inductor. And since it was already large, let's say we skip this possibility. Another one would have been creating an LC filter at the output, or placing multiple capacitors in parallel to achieve the capacitance desired. And this is what we have done. Also, we try to use, in this case, polymers capacitor, because they are quite good in terms of minimum equivalent series resistance. In the case before for input, we use ceramic capacitor because they have lower ripple current. In this case, polymers capacitor are also good because with low ESR we try to increase power efficiency. Now I'll let the word to Enrico for protection and sensor.
Okay, now we are going to talk about voltage sensors. We have applied the same schematic both at the input and output side. We have some constraints on the analog to digital converter pins because the input, these pins can support at maximum 4 volt and the maximum input current is 5 milliampere. Based on these constraints, we have to use a voltage divider to measure the input voltage of 48 volt, so to decrease it. Then we have a buffer and a current limiting resistor which is the R19 in the figure to reduce the current which enters the analog to digital converter pin. Below the figure we have the formula to calculate the reference voltage of 48 volt. And at the output side, we have exactly the same schematic with the different resistor values because in this case we want to measure 13.6 volt instead of 48. Then for what concerns current measurement, at the input side we have used a shunt resistor with a very low resistance value to have a low voltage drop across it. Then through an instrumentation amplifier we have increase the voltage, and also here we have the use of a current limiting resistor which is R23 to decrease the input current to the analog to digital converter pin. Below the figure we have also here the formula to calculate the current which passes through the shunt resistor. At the output side the DC-DC converter implements the constant current operation, so the circuit that you can see from the slide is taken from the datasheet, where we have a sensor resistor, also here an amplifier, a buffer, and then from the IMON pin we measure through the MCU the voltage that we have on this pin, which is from the simulations 0.45 volt at the steady state, and so the average output current in this case is 7.5 ampere. Then about the temperature sensors, we have used RTDs for the most dissipative components inside our circuit, so for the 2 inductors, for the DC-DC and the 2 MOSFETs. As you can see from the figure, we have placed the RTDs as near as possible to the components for which we want to measure the temperature. The measuring principle is a ratiometric temperature measurement where the RTD resistance is a function of the reference resistor, and the resistance temperature relation is in the figure in the slide, where when the temperature is lower than 0 Celsius degree, we have a 4th order equation, otherwise we have a 2nd order equation, which is easier. Then for what about the circuit protection for our schematic, in the slide you can see in the upper part the circuit protection for the input side, while in the lower part the circuit protection for the output side. We have placed TVS diodes for ESD protections. Then we have a diode only at the input side for inverse current battery, and PTCs for inrush current, which are placed in series with our circuit, both at the input and output side. Finally, about the circuit protection, we have also the overvoltage protection. Our DC-DC controller can work at maximum with an input voltage of 60 volt, and when the voltage is higher than 60 volt, we have a pin which is called in the slide of low pin, to disable the DC-DC controller in the moment in which we have a voltage which is higher than 60 volt. To calculate the resistors, we have used the formula that is at the right side of the figure, which is taken from the datasheet. Now I leave the word to Michele, who will talk about the software.
So, for what concerns the software, we have decided to implement a code that respected the fundamental principle of programming. In particular, we focused our attention on reliability, testability, and efficiency, but the main focus was on modularity. Modularity because our code has been written according generic function in order to have a code easy to manage, easy to test, and in future, if we want to add some feature, we have just to modify the single function and not the entire code. This permitted us to achieve the maintainability, that is one of the most important part in programming microcontrollers. So this is an overview of our system, and the data can go in both directions. And we decided to divide our system into parts, transmitter side and receiver side. But for both the programs, we implemented interrupts with different priorities and the DMA, not because we had some power consumption constraint, but because we wanted to have an MCU as much as possible in sleep mode, and have it in normal mode only if there are operations to do. For what concerns the hardware, we used STM32Cube IDE, that is a software that permits to set all the peripherals and generate the basic code. And here we exploit the modularity because both sides uses same or similar peripherals. For example, the external clock, the big scan, GPIO's output, and the debug serial while for the testing. At the transmitter side, we set also the ADC with the DMA, and at the receiver side, the USART DMA and the user button. In this slide, we will show you just a simplified overview of our flowchart and the structure of the firmware, in particular the transmitter side. And we start with the initialization of the peripherals and the start of all the peripherals, and the check for some errors. If some errors occurs, we generate a log file and stop the system. Otherwise, we put the MCU in sleep mode and wait for interrupt. But at the same time, the DMA starts, and it starts to read ADC values. And when it finishes, we will raise an interrupt, and the MCU wake up and check for the data. If the data presents error, we code this error and send that on CAN bus. Otherwise, if the error is hard, we stop the system and generate a log file. Otherwise, we send directly the messages on CAN bus. At this point, the CAN transmission can start and start the callback. But if an RX callback will raise an interrupt, we have to stop our transmission and manage this error because the priority of RX is higher with respect to the other. This is the receiver side, and the code is pretty similar due to the modularity. The only thing that we changed are the decoding of the messages and the priorities between CAN TX and RX and with the DMA. So here we decode the message and send them on WART, and when these messages are decoded, we start the DMA and perform this data at the receiver side with a terminal and a GUI interface. Now my colleague Nalanda continue with the explanation of this GUI interface and the CAN message.
Now I will be talking about the software components of CAN communication, ADC, and a user interface which we use for monitoring and testing in the last phase of the project. So to begin with, first it is very necessary to make the appropriate filter settings in order to receive the correct messages on the receiver side. So for this we have to set the appropriate filter ID and mask ID, and all the incoming messages are stored in the receiver side FIFO. There were some limitations on the underlying protocols, namely CAN and UART. So to begin with, the data that we could transmit over CAN was just 8 bytes, and we had 8 sensors and a lot of data at a single time. Then all the values that the sensors generated were decimal values, and there were also some negative values. So as a solution, solution for the first limitation, we transmitted the data of 2 sensors at a time. For the second limitation, we developed functions that converted the float data into integer data for transmission on CAN, and where UART communication was concerned, the float data was converted to string data and transmitted over UART. And for transmission of negative values, we developed a function using the offset technique. And all our message transmission was priority based, so the error messages got the highest priority. This was followed by the ADC data, the sensor data, and all the remaining data got the lowest priority. As we can see that there are 8 sensors and a lot of data at the ADC. So there is a chance that we could lose some data. In order to avoid this, as a solution, we used DMA with ADC. So when an ADC channel finishes conversion, a DMA request is raised and data is transferred to the memory, which is then further processed to be transferred over UART. Now, in the very last stage, where we wanted to monitor if our system is functioning properly, and we wanted to see what are the values of the input current and voltage, output current and voltage, and the temperatures. We developed a very simple GUI with the help of which we could monitor all the data in one place. The features of this user interface is that you can see all the logs, all the information, and you can view it also in the graphical form. Both these are real time. Also, another thing, if we wish to revisit some values, we can view them from a CSV file. All these values are saved in the backend in a CSV file. This user interface also told us if any particular dissipating element is overheating. So also if we were providing too much input current. So there was a particular formatting for these error values. So we can see that each error begins with the first alphabet E, which is followed by I, V, and T for current, voltage, and temperature, which is followed by IN for input or inductor, OU for output, MO for MOSFET, DC for the DC-DC controller IC, and ST for the STM32 IC. So in this way, this GUI or user interface helped us identify which area of the DC-DC circuit is working properly and which is not working properly. And now I hand over to Matteo.
So thanks, Nalanda. Good morning, everyone. So now we're going to finish talking about the hardware and software test. In particular, we attempted the hardware test, in particular in the last week, and we started from the second board, since it was the easier one. It was very straightforward. We just checked the boundary scan and diode test, and testing from 0 to 12 volt with no issues at all. We were just powering just fine both the two transceivers that we can see in the figure in violet, and with the pins to power our MCU from STM. For what concerns instead the main board, which was the very complex one, we started with the boundary scan and the diode test, and with a test from 2.5 to 48 volt, we unfortunately got no output. So in particular, from there, we started debugging the whole circuit, trying to understand on the main component if they were powered enough, and checking the power along the line, and we made sure that the DC-DC controller was in fact on. And since it was, we then also, besides all of the main components, we found out that there was an asymmetry on the two switching MOSFETs. In particular, we identified the problem in one of the two pins that are the gate drivers of our DC-DC controller, and while on the Q1 MOSFET, which is the top one in the right figure, was indeed powered, so we read 7.2 volts. On the other MOSFET, the Q2, we just read 0 volts. So the TG pin was the actually faulty pin from the controller. These tests were performed at 25 volt input, and in fact, we read about 24 volts on the drain of the Q2 MOSFET, since is on the main line of the circuit. So the power was there, but it was not switching as properly, of course. The right-away solution was, of course, to change the DC-DC controller, as we had one in stock, but unfortunately, due to lack of time, we decided to further proceed with further tests and experiments. The main reason is that we had a very complex board. There was a high risk of damaging other components, and also due to maybe problems of the design or other parts of the circuit, we wanted to experiment and test the circuit without the fault pin that was causing zero output directly in the output line. So we just did an experiment without the fault pin and connecting the output line directly to the drain of the lower MOSFET that was already functioning. And with this in mind, up to 48 volt, we just got this output of 1.97. This wasn't a random experiment as it is. We just did on the last day of the lab a very quick LT-SPICE simulation just to check before putting our hands on the main board and continuously checking lots of data around the main circuit. For what concerns inside the software test, we performed a CAN communication line, as Michele previously said. On the right top corner, we can see the CAN bits during the transmission on the oscilloscope and the main system at the bottom. These are our two transmitter and receiver MCUs, and the problem that we had was related to some synchronization issues that we can see in red, highlighted in red in the top left figure when data failed. And we approached this problem with restarting of the CAN software function inside of STM32IDE. And to solve another issue, we did the same approach for what concerns the DMA that was handling the ADC conversion. Since we have multi-ADC conversion happening at the same time, DMA was a must, and sometimes we understood that it was too fast for the ADC conversion pins, especially for the internal channel temperature of the STM, since it needed a small amount of microseconds to actually read with a 1 degree of accuracy. And so we also here restarted the DMA periodically to continuously check and to obtain continuous requests. For what concerns the ADC test, instead, we checked with various trimmers and other resistors if the conversion could actually happen simultaneously. And indeed, we found some faulty trimmers which gave an offset in the internal temperature sensor. And once changed that, we could see every data red. Okay, to summarize what we've accomplished so far, we can conclude with these 5 fundamental pillars. We surely have to admit that we did not have enough time based maybe on our organization of the whole process. On the main part, we could have improved our project, maybe including the second PCB that we are using basically just to power 3 modules. We could have been implemented on the main board itself, just to reduce some cost and to have a unique board. But this was possible only if maybe we could have done a simpler design of the PCB, which needed a simpler maybe DC-DC controller. And it's important to remark the fact that in the condition where we had, there was a chip shortage, and so we had to compromise with the availability, in this case, of the DigiKey stocks. I'm very proud of our team. In particular, we were very strong in team communication, but most of all, we always had frequently updates on different problems from different nature. We always had a seat to understand and to debug either the software or the hardware part. And so we are, even though the results looks not, it doesn't look very promising, we are very proud of what we accomplished so far. Thank you to everyone. If you have questions, feel free to ask them. And if you want, in the meantime, maybe Michele can show you a video explanation of how the software can work in total, you can say.
All right, thank you. Thank you very much. Any question first? I mean, because you use your 30 minutes, so if we start now a demo of the
yes.
software, then
Yeah, that's
you
why
it
I
should
asked,
be very
yes.
short. If it is very short, it's okay. 2 minutes, okay. We can do it. Okay. No, no.
What attacchi qua?
No.
Aspetta, usare... Okay, thank you.
So there are no questions from our side, so if we want to switch and move to group 2.
Good morning to everyone. I'm Esposito Luca and I'm going to present our project about the CDC converter 48 volt to 48 volts to 13.6 volts. This is the agenda of our presentation. We are starting with the project management. Then we are going to illustrate the hardware and software design, and after that we finish our presentation explaining the test and the validation and all the results that we obtained at the end of the project. So let's start with the project management and with the team organization. So this is just a quick slide to illustrate which person do what during the project. So I'm the project manager, and I manage all the activities and support the report and other activities. There are two people that are involved in the hardware design, that are Palombo Davide and Rebecca Gabriele. In particular, Palombo Davide managed the controller and the converter design and support the PCB design, which is the main main task of Gabriele. And the other two people that there are Deida Federico and Savino Giuseppe, manage the software and the HMI interface. And last but not least, Federico, that manage all the documentation, and in particular the writing of the report. We adopt a bimodal strategy because we think that in order to correct errors that we can discover during the test process, we can go back to the design phase and try to fix that. However, this is a strategy that was not possible to adopt during the last phase in last week, because the deadline was very close, and we are not able to fix some problems that we discover on the PCB. This is our work breakdown structure, and as you can see, we start at the beginning design and macro planning of the activities, and how to organize all the work, and to write all the documentation that was required by our professor. After that, we start with the defined design phases, and we work in parallel with hardware and software. The hardware requires a converted design, a protection circuit design, the sensors, and the interface with the interface with the CAN, with the communication line, and all what regards the MCU design, so the coding and the debug. After that, when we have a clear idea of what was the circuit, we write the BOM, the bill of materials, and during the BOM we search a lot of components, and as all of us knows, nowadays it's very complex to find the correct components for each scope of the circuit. So it was the main problem of our project, let's say. After that, we passed through the production phase, where we made the PCB and all the integration with the other circuits. And in parallel, we work on the software, so on the MCU flashing and the CAN and the HMI interfacing. At the end, we test and validate all the boards during the laboratory session. This is just a small Gantt chart that illustrates what we did in these 3 months. And as you can see, the first week we do an overall planning of the activities, and on October we start with the hardware and software design, and in November we start with the PCB design, once we know that the simulation of the hardware and the software works well. And during the last 3 weeks we dedicate our time on the hardware and software validation. I want to highlight that during all the process we write the report in order to keep a clear idea of what we are doing, what we was doing. Briefly, I want to talk about the budget management, and I want to highlight the software that costs zero, because we use all free license software, and we don't spend the money on that. And so the overall cost is under the 100 of euros that was the budget imposed by our stakeholders. This is just a list of the software we used. We use Altium Designer to design the PCB and LTSpice to simulate the controller in particular, and System32 Cube ID for the software part, for the coding and the debugging, PyCharm as well. Overleaf is the software that we use to write the report in LaTeX, and Office 365 to manage all the documentation. And now I leave the stage to Federico Zucchini.
Good morning to everyone. Now I'm going to talk about the hardware design and in specific about the protection circuits and the EMI filter. This is our functional block scheme. We can see the requirements in the left. We had to have an output voltage of 13.6 volt and an output power of 100 watt. All the components that we choose have to have a maximum operating temperature of at least 125 Celsius degree. We have a power supply for the power line of 48 volt, and we have a power supply for the signal line of 13.6 volt. And we use a voltage regulator to obtain the 3 volt to supply the microcontroller unit. And then we have 3 types of sensor: temperature sensor, voltage sensor, and current sensor. As a type of communication, we implemented the CAN communication. The hardware choices that we had to make was to choose the protection circuits, a back controller, a microcontroller unit, and all the sensor. To obtain an overvoltage and overcurrent protection at the input, we choose to use the LT4363 from analog devices. This IC works as both overvoltage and overcurrent protection. We had to set a reference voltage, and we decided to choose to have this value of 49 volt. An overvoltage level and an undervoltage level. The overvoltage is equal to 60 volt and the undervoltage is equal to 30 volt. And a maximum current that we choose to set to 5 ampere. The maximum current is set in this case by the resistor R1 that is placed between the pin sense and the pin output. The reference voltage is set by resistor R2 and R3, and the overvoltage and undervoltage level are set by the resistor R5, R6, and R7. The meaning of this voltage are that the output voltage can't go above the reference level, so can't go above 49 volts, and if the input voltage goes above the overvoltage, the component shut down, and even if the voltage goes beneath the undervoltage level, the device shut down. Then we had to choose some components for the inrush current protection and the ESD protection. For the inrush current protection, we decided to use two components, both from Caterham devices, and they are the NTC thermistors. We put the one with the maximum current value of 3 ampere at the input, and the one with the maximum current value of 8 ampere at the output. We choose these two values to satisfy the power requirement given by the stakeholders. Then, as ESD protection, we used 3 different devices, 2 from Panasonic and 1 from Vishay Semiconductors. The 2 from Panasonic are placed one at the input of the power line and one at the output of the power line, and the one from Vishay Semiconductor is placed at the input of the signal line. Then we choose to place one MEI filter at the input of the signal line, and is an LC pi type of filter, and we use this kind of device to eliminate all the high frequency components on the line. The cutoff frequency of the device we choose is 10 megahertz, and then we decide to use this kind of device even though it was not required by the specific given by the stakeholder. And then now Davide is going to talk about converter and sensors.
Yeah, good morning everyone, and now we are going to talk about the choice of converter and sensor. Basically, the guideline that we follow in all the project is to respect the trade-off between efficiency and the cost. Efficiency from a technical point of view, and cost in order to respect the budget limit of a university. In fact, for that reason, we start to think about the first controller, LTC 3810. In that case, the pros of the choice is the high efficiency due to the fact that it is a synchronous buck controller. So 2 MOSFET instead of 1, it means lower voltage drop and lower power losses. But the disadvantage in that case are a lot. In particular, the first is the high circuit complexity, because to manage 2 MOSFET instead of 1, the components around the buck rise. The second is the no availability on the market of it. So the availability of it is very, very poor, and could be the risk that the day of the order we don't find it on the key. And third is the high cost. For that, we decide to discard that idea, and we move to the second buck that we think about, that is the LTC 3864. In that case, the complexity of the circuit is very low due to the fact it's not a synchronous buck, but it's a standard buck with 1 diode, 1 MOSFET, and 1 inductor. Also, the availability of it is not poor, but it's higher, so it is a good advantage. But then the cons are the low efficiency, because in the design, in that case, there is a P-channel MOSFET, so low mobility of the carriers, higher power losses, but in that case, the availability of the P-channel MOSFET is poor on the market, and so we discard also that idea. And finally, we think about the LT3724 buck controller, and in that case, all the trade-off, the efficiency and the cost viewpoint are respected, because the complexity of the circuit is very, very low. Also, the efficiency for the purpose of our project is reasonable, around 95%. And also, the availability and the cost is very, very low, and so we decided to adopt that buck controller. From that slide, we can see that from the choice that we made before, we are able to respect both the constraint regarding the output voltage, so we are able to obtain the desired 13.6 volt, but also the output powers that are from the requirements 100 watts. Then we start to think about the MCU and what could be the best MCU in order to manage the controller and the sensor. And we choose an STM32L4 for mainly 4 reasons. The first is the availability on the market of it, so it's very easy to find and to buy it. The second, because in that case, it contains an embedded CAN controller, and in that case, we avoid to buy another module to implement that functionality. Also, in our group, we have just a debugger, and we can reuse it in order to interface with CAN. And also because some of us had just a previous experience in the STM environment. Then we start to design and think about the sensor, and we start from the temperature sensor. In that case, we choose an LMT86 sensor. This sensor is able to work in a temperature range from minus 50 degrees Celsius to 150 degrees Celsius, and in that case we are able to respect another requirements of the project. Also, we choose it because the availability on the market is high, and also because the cost is very low, and also with that component we are able also to respect the automotive compliance documentation. And we decided to measure more or less the three more critical components in the circuit, that are the MOSFET, the inductor, and the diode part. Then we move to the current sensor. In that case, we use a shunt resistor with an order of milliohm, so a very low value. And in order to measure how much current flow around the resistor, we use an ENA 293 instrumentation amplifier in order to be able to read the voltage that falls across the resistor, and in particular to be able the MCU to read that value. Another option that we could use could be the Hall effect sensor, but for cost reason we decided to avoid that option, and we use heat, that from our point of view it could be more easier to manage, but also the cost is lower. And then we move to the voltage sensor. In that case, we use a simple resistor divider with a buffer with a unit gain. The two resistors that we choose is a resistor of order of kiloohm, and through the buffer we are able to move down the output impedance in order to be readable the voltage that fall across the resistor by the MCU. And then we move to the software part with Giuseppe.
Good morning. Regarding the software design, we basically follow this path in which we started from sensors, in particular analog sensors that are sampled at a constant interval of time, and thanks to the DMA we load the oncoming data on the MSU, so we can elaborate them in order to convert and get the final values that are finally sent on canvas. Regarding to the MCU configuration, it has been configured in this way, with the green pin that are used to connect the sensors, 2 pins for CAN communication, 3 pins for the serial debug that has been used to debug, test, and load firmware. And finally, we used just one pin in order to switch on or switch off the controller according to the constraints that we have. Basically, starting from the starting point, we have a waiting phase in which allow each hardware component to set up in order to work after only with consistent data. After that, we have an initialization phase in which we set up each component of the MSU, like CAN module, DMA, GPIO module, and so on, so that the CAN module can start, and also the while loop will start. For each cycle of the while loop, we get new data coming from the DMA, and check that parameters in order to respect the constraints, and if some constraints is not respected, it switch off or switch on according to the previous situation the controller. Finally, it sends data on CAN bus, and for each cycle we have 0.5 second of delay in order to have on the receiving side consistent data. Taking a look more in details about the communication between the sensors and the DMA, basically the ADC module, the analog digital converter module, makes a DMA request to the DMA in order to load the data coming from the sensors on the SRAM by using an advanced high-performance bus and bus matrix, in which we used the configuration explained in the slides with 12 bits resolution and 8 megahertz of frequency to the ADC. Regarding to the conversions, once the new data arrives on the processor, we can see in the upper part of the slides an example. Basically, according to the formulas, we can convert them in order to have the final value that are an example in the bottom part of the slides. And for instance, as we can see, there are no floating values, as we know, because on CAN bus we prefer to manage only integer values, so they are multiplied by a factor of 10 that are after divided by the same factor, and also the negative values are managed by using an offset value that are basically managed also on the receiving side. So regarding the communication, we'll talk Federico.
Hello everyone, I am the responsible for the software design in the part of the CAN interface and the HMI. So our data flow, starting from the right to the left, we have our MCU, in which we have obviously our sensor that sends the data to the CAN bus, and from the receiver side we have a transceiver that in order to work needs a Linux subsystem, so we used a Raspberry Pi as a gateway ECU, and by using the Raspberry Pi we use the Wi-Fi and in order to send the data in, let's say, in a remote way to our computer. So we decided to make not just our say voltage control unit, but also a kind of diagnostic tool, like I don't know, something that it's used in for the debugging purposes. And in particular, why the CAN bus and why the choice of the Wi-Fi? First of all, the CAN bus, as we all know, it's very used in the automotive domain, and also it's very robust. For our purposes, was the best protocol that we could use, since we were working with sensor. And the Wi-Fi was used because in this way we could have the remote data monitoring and also in real time. And this is important, since we want to see what is happening right now in our control unit. And since our Raspberry Pi is not doing some kind of data manipulation, but it's just a gateway that routes the data, it was, let's say, a good standard to use. And talking about the CAN bus, so the main part of our communication, in this slide we can see how the layout of the message is done. And we know that in our CAN message we have at most 64 bits. So we used the length of our message at its best in order to not congest the bus, and so having a bus load as low as possible. And in particular, we used 3 messages to send 8 signals. So regarding the temperature sensors, we had just one message in which we put 4 signals of the temperature, which you can see. So we have the temperature sensor of the MOSFET, of the diode, of the inductor, and of the internal temperature of the MCU. And here it's important to see how we manage the different type of messages. So when we had four signals regarding some kind of sensor, we used one message, and in particular here show the current sensor in which we had just two signals that we didn't use 64 bits, but we used 32 bits, so we exploit it at its best. And in order to send the data from the Raspberry Pi to the PC, we use the UDP protocol. So we use the UDP protocol because as I said before, all the data manipulation is not done by the Raspberry Pi, and it's done by the MCU itself. So the data is just routing from a point to another point, and it's not manipulated when it's going from an ECU to another ECU. So here you can see a simple communication in Python, in which pretty much every protocol which works with socket has, so with the IP and with the port. And this is a simple example in which we sent a hello world from the Raspberry Pi to our PC, and we received obviously the string. Here we have our HMI, in which we pass from waiting for the ECU data, and then we receive all the parameters that we need to check in order to be sure that that our voltage control unit is working properly. And this is a very simple HMI, but for our purposes was very good, because in this way we could see the data in real time and also remotely, and it was the best choice from our point of view. And now I let Gabriele talk about the test and validation. Thank you.
Thank you. So now we will talk about the PCB testing and design and validation. This is how we will proceed. We will see, first of all, a bit of PCB design, then testing, what problem we have found and what solution there are, and some conclusion of the project. The first choice that we had to make by designing the PCB is if it will be a single board or a multi-board PCB. There are pros and cons of both of them. With single board PCB, the pros are that we have lower dimensions since it's a single board, but the cost will arise, and if some components will break, its replacement will be more difficult. Instead, with a multi-board PCB, we have a lower cost since the PCB are more than one, but if they have different composition, the cost can be lowered and the component replacement can be easier. But the dimension instead, since they are more than one, will be bigger. So we have decided to proceed with a multi-board PCB, and the first that we have designed was the logic board PCB, which is a two-layer one, on which the top layer there are the MCU and all components. And the MCU, since it's the core of this PCB, is in the middle, and all around of it there are the filtering capacitors placed near the voltage supply pin. And we have also paid attention to make a differential routing for the CAN signals due to do not have some interference or do not have some interference on it. And we have also a JTAG connector that uses the same pin as the SVT protocol that has been used to program the MCU. The bottom plane of this PCB is just the ground plane with the at least track as route as possible to make the ground plane as smooth as we can. Then we designed the power board PCB, which is also in this case a two-layer PCB, and we try to keep the input and the output distance one from each other, and we based our design on the current loop solution. So we try to close the loop of the current in the smooth ways as possible, in the small space as we can. It's in particular for the transistor that is a switching route, so we have high frequency signal on it. And since the PCB this circuit needs to handle high current, we have managed them with power planes due to the fact that normal routing do not withstand so high current at the order of the tens of amps, at 7-8 amps. After we have designed the PCBs, we have tested them, both the logic board and the power board. As we can see, the logic board has been tested for continuity, which was fine, as well as the power supply, the MCU programming, and sensor acquisition and CAN connectivity. Instead, on the power board, we have that both the power supply and continuity were okay, but the output voltage was not okay. We were stuck at 1.5 volts, so we do not proceed with further testing, but we have tried to investigate why it is not working. So we have tried some tests, and we have reached some possible causes of failures. That since one of the core of the project was the MOSFET, and the output was not given, the possible solution was that the MOSFET was faulty, or some capacitors are not are broken. But there can also be a PCB routing error, so there can be some bottleneck or some soldering problem due to the fact that we have chosen, due to inexperience, two small components to be hand soldered, so do not, and maybe there are some not well done soldering. So in conclusion, that we have some challenges and solutions that we have faced that are the chip crunch of the pandemic, and we have solved that by choosing not automotive compliance component. But we were also, first of all, not possible to meet each other in person due to the fact that we are all from a part of Italy. Some of one are already working, so we have managed by dividing us in subgroups that can work independently and have virtual meetings. We used free license software to solve that, and mandatory deadlines due to the fact there are no physical meetings, but only virtual. Then we have some problem in the last phase, that I guess the PCB assembly, that we have asked for an external help, or some wrong track on the PCB that we have manually adjusted them, trying to see where the problem was. And there was some sensors offset problems that has been solved by experimentally adjusting them, or on the access point for the HMI interface, and it has been solved by reinstalling the operating system of the Raspberry Pi. Thank you for the attention. If there are questions.
Thank you. Thank you very much. Even the other students, if they have questions, they can actually ask. Okay, no problem.
Sorry?
And I was asking to the other students in case they have questions. No.
No. If possible, there is a brief simulation of the CAN transmission,
right.
Or maybe we can make it at the end of
if
the...
If it is short, like 1-2 minutes, no more, then we can do it now, otherwise we do it later. Is it long?
Yeah. Maybe we may. Facciamo dopo.
Stacca? Sì, lo facciamo
Okay.
vedere.
Basically, we have the logic board with the analog sensor connected, as we were in the real scenario with the power device, with the power board, sorry, and basically what we can see.
Stacca?
Huh?
Okay. So now we are going to start the script. As you can see, we are not near to the control unit. So we start, we wait for the data, and when we sorry, and when we turn on the ECU, you can see that we're gonna receive the data.
Okay, data.
So we have a stream of data, and we can see real time remotely what is happening in our control unit. Yeah, that's it.
Era arrivato prima per il terzo, non l'ho mandato la seconda volta, non ce l'avete? Io sul terzo gruppo che ho mandato con il... l'ho mandato. Vabbè, ma è solo il titolo. Sì. Fate un reload perché l'avevo corretto, probabilmente se solo le ricaricate è stato corretto, vedete se...
Quindi dobbiamo cambiare dal tuo? Sì, lo lascio qua.
All right, let's move to the third group now. Last but not least.
Come ci metti? Qua. Qua sono io, tu secondo sei. Lo vuoi che metti in esterni? Però in esterni va su tutti. Ah no, sì, va in esterni. A me, vabbè. Ti senti? Vado?
Okay, good morning everyone. I am Alessandro Tavosa and I am the manager of this group for the design of an F1 electronic unit. According to the requirements of this project that my colleagues already explained before, we have decided to divide our job in a pyramidal structure. At the top there's me, the team leader, which I'm responsible for all the organization part and the production of the documentation that needs to be performed in order to keep track of all the improvements, all the decisions, and everything that concerns the development of this project. Just below me, there's the Chief Technical Officer, which is Simone Pattarozzi. He was responsible for all the management and technical decisions related to the two sub-departments of the software and hardware department. In particular, for the software one, we had two different components. Michele Ciaramicoli, which was responsible for the MCU development and the firmware development, and Lino Mastronardi for the realization of the bridge and the user interface provided with our system. From the other side, we had Francesco Marani and Roberto Sanna, which were responsible for the realization of the board, the acquiring of the components, and the soldering of the final system. In order to organize our job, we used two main tools. The first one was the work breakdown structure. As you can see here in the slide, we can identify 4 different main branches. The first one is related to the project management. Is the only one that goes in parallel with all the others, since the documentation and all the revisions of the job must be performed on runtime. The other 2 branches, which are the development ones, the hardware one and the software and firmware. The first one, we can divide it in the development of the power node, the development of the control one, and the realization of the bridge board. From the firmware point of view, we had simply the definition of the control node with the realization of the code of the MCU and the realization of the LabVIEW user interface. At the end, the fourth branch is related to the validation of all the system, which was performed by all the team members in order to verify if the job done before was actually working as expected. The second visual tool and organizing tool that we have used is obviously a Gantt chart that defines all the deadlines that were taken into consideration during this development project. We decided to realize a Gantt chart considering conservative deadlines in order not to affect the overall working of the project in case of any deadline miss. In particular, we had only just one related to the design and the order of the power PCBs. For what concerns our development model, we've selected the V model one and not the waterfall, since we thought that the best way to develop this project was using something that can be reversed. So after defining the 4 main steps, the first one, the identification of the requirements, then the analysis and the design of the whole device, and at the end, the implementation, we can actually start the validation part, so the unit testing of all the single components that build the overall device, the integration, and at the end, the acceptance test. This particular type of model was used because of its high flexibility and possibility to check every time a new step is done, going backwards, looking at the requirements that we were using at the beginning. From the cost point of view, all of them started with a budget cap of 100 euros. This particular limitation brought to an intense analysis related to try to maximize the performance of the system and also minimizing the cost. We all know well that the actual situation of the electronic market is affected by chip shortage, so this was a particular challenge to take into account when buying or choosing any component. For this reason, another strategy used by this group was reuse and the implementation of personal properties. Members of the group had the possibility to give to the group the availability of connectors and cables, and also the availability of a 3D printer for realizing any support or device that we need during the development. At the end, we have estimated a total amount of money of 94 euros with a fund saving of almost 40 euros.
Hello everyone, my name is Simone Pattarozzi and I'm going to describe this slide which depicts a simplified structure of our system. In particular, starting from the left, we find the interface and the bridge subsystems, which is, even if not part of the actual DC-DC, is extremely useful for data visualization produced by the device. Then, in the middle of the image, we find the MCU, which is the core of the control board, and this particular device is used to manage the CAN bus communication, the sensing acquisitions of all the sensors placed around the power board, and the finite state machine handling which drives the DC-DC, which is the last and the most important part of the system, which will be discussed in detail later on, and all its subsystems, which enable its correct operation. In particular, a precharge circuit, a voltage feedback, which is possible to tune from software in order to change the output voltage if needed, and voltage, temperature, and current sensing subsystems, and the safety mechanisms which ensure the correct operation of the system even under fault conditions. In particular, these conditions were analyzed through an FMEA document which is present into the documentation.
For our project, we design a DC-DC synchronous buck converter that should be described in 3 main stages. The first one is the input, characterized by a capacitive bank that allowed us to avoid input fluctuances and noise, but introduce some high current spike. In order to avoid this spike, we design a precharge circuit characterized by a controller that is controlled by the MCU and 2 MOSFET. The main stage is the DC-DC that is composed by an LTC7801 controller and 2 power MOSFET and inductors that convert from the input of 48 volts to 13.6 volts at output. The output stage is basically the same of the input, but with different functionalities. It connects and disconnects the output, the load, if malfunctions happens. For what concerns the validation of this circuit via software, we use LT-Spice, and after, as we can see, after at that time of few seconds, the output reached 13.6 volts. That time is basically the precharge time in which the capacitor are charged and then the conversion can start. With this setup, we evaluate an efficiency of 19.93.4%. That should be for sure improved.
Hi, I'm Francesco, and I'm going to tell about all the subsystem of the circuits. Here we have the voltage feedback. It is a control feedback line of the DC-DC stage and have a constant output voltage of 13.6 volts. It is made only by the resistance of the voltage divider, so we have the possibility to have a variable output voltage in a range from 10 volts to 15 volts, software controlled, changing the resistance value of the internal resistance of the MCP component, that is a digital potentiometer with an SPI interface. In the right, we have the trend of the output voltage, changing the internal resistance of the component. Now I'm going to enter in details about the 3 sensor circuits: the temperature, the voltage, and the current measurement. The temperature measurement circuits, it is based on the LM339 component. It is an open collector pump. We have trimmers and we have NTC thermistors that sense the temperature and provide an hardware switch off. This circuit is divided in the 2 boards. We have the thermistor, as we can see in the figure below, in these 4 sides to provide a temperature sense, and all the other components in the control board to protect them from the short circuits with a voltage supply. We have the voltage measurement circuits. His aim is to measure voltage in 3 different locations and protect all the components from overvoltage and voltage spikes. In particular, the first 2 circuits, voltage 1 and voltage 2, control the working of the precharge circuits, and the voltage 3 control the correctness of the output voltage of the entire circuits, that is 13.6 volts. In the current measurement, the circuits sense the current by taking as input the shunt voltage measurement read by the MCU. We have a shunt resistor that have a very small resistance value, so we have to implement a circuit with in a 240 that can amplify the voltage with high level of accuracy. An important feature is done by the voltage reference in the component that allows us to implement a reverse current protection. Now I'm going to tell about the safety circuits. The first is the overcurrent protection. It is based on the LT 1910 in the output stage of the DC-DC, and it protects the system against output short circuits or overcurrent. We have the enable line based on two stages, the charge pump and the DC-DC enable. It allows us to control both software and hardware, the switching off and on of the DC-DC. And then we have the fuse and the fuse state that provides a complete protection from all the systems and control the well working of the fuse.
For what concerns the communication with the external ECU, we decided to use the CAN bus. This is like the standard for the automotive application. The controller is integrated in the microcontroller, while the transceiver has to be placed on the motherboard. We choose a baud rate of 125 kilobits per second for our application because in this case was enough. As I said, we used a transceiver mounted on the board provided by Texas Instruments, and we placed some TVS diodes and capacitors to provide protection to the transceiver from the noise that can happen on the CAN high and the CAN low line. Also, we implemented a programmable termination controlled by software. That basically there are two optorelays that activate or deactivate the 120 ohm termination of the CAN bus. So this makes us able to decide whether or not the node has to be considered a termination node for the CAN bus or not.
For what concern the PCB design, we use Eagle, and we decide for budget limitation to realize two different boards. The power board, that is the most difficult to design because all the components are bigger and experience high temperature. For this reason, we design three equivalent equipotential pads, the V-in, the voltage 2, and N30. The two boards are connected through an R-Win. And for what concerns the control board, it is quite simple because we have more space and less components and smaller, and we manage it as we want, basically. We design the two boards following the good law in order to design a board. For the thermal analysis, because the temperature are a sensible problem, we decide to do analysis with Fusion 360. For decrease the computational complexity, we decide to do the analysis only with the MOSFET and the inductor and the three pads. The results are, we think, quite distant from the reality. As we can see, the pads don't work with as we expect, but it seems that they conduct only for proximity to components. This is the final prototype.
Now I will talk a little bit about the firmware design that controls everything. So basically we got two routines that are activated by interrupts. The timer 3 interrupt activates the ADC that sends the inputs, and the DMA moves the data from the peripherals to the memory. Then the conversion to the actual values, so the temperature values, the current values, and the voltages values are performed. Plus, we set a bunch of flags for errors and warnings. So we got some threshold for all the measurements, and we set some errors or some warnings if we find some problem. The other routine is the one activated by the CAN RX interrupt. So basically, when a message from the ECU arrives, this interrupt fires. It is a 10 Hz signal, and basically the ECU sends this message containing the state requested for the CDC. Of course, the data read and the state wanted from the ECU affects the finished state machine selection, state selection, so the operating condition of the DC-DC. Last, we have a 10 Hz routine triggered by the timer one that basically sends the messages over CAN bus. Few words about how the finished state machine works. We got an initial state that is lived as soon as first DC conversion is performed. We go in the pre-charge state where we're waiting for the pre-charge to happen. And so when the pre-charge is complete and when we receive a run message from the ECU, we can go in the normal operating mode, so we can switch off the DC-DC, and now we are in run mode. Here we constantly check for error flags activations and for the heartbeat, so for the presence of the message from the ECU. And if something happens, we go in the error shutdown mode where the DC-DC is switched off another time. And we stay here until a reset is received from the ECU and the process can start again. We also got a standalone routine that basically, as I said before, sends the message. And here we reported the CAN database. And as we said, we communicated the errors, all the temperatures, all the voltages, the currents, and also the warnings. For this task, we used an STM32F103C8 microcontroller. And it is not so powerful, but it was enough for this kind of application. And here we reported the pinout, so there are all the input for the ADC and all the other inputs that are needed to have the system working as intended.
A user interface was used in order to visualize messages sent by the DC-DC and in order to simulate an ECU, a vehicle ECU, in order that exchange messages with the DC-DC. We decided to use a bridge to convert CAN messages into UART messages to let the DC-DC communicate with the laptop. But we have to state that we have developed but not realized the bridge due to budget constraint. In the figure you can see the frame that the DC-DC sends to the laptop, and is composed by 11 bytes. First byte of identification that contains the ASCII values of the character A, B, C, D, or E, that indicates respectively a set of temperature messages number 1, set temperature messages number 2, output voltage and output current measurements, and set of warnings and a set of errors. The 8 following bytes contain the payload of are exactly the payload of the CAN, and then we have two end of frame bytes that contains the hash value of the dollar symbol that are used in order, because when we connect the DC-DC to the bridge to the laptop, it is possible that it is already sending messages. So we use the end of frame to be sure that our laptop will read correctly one frame. And then we have our interface that is developed in LabVIEW. It is divided mainly in two parts. The first part on the top that allows the user to decide the baud rate, the voltage set point in the request mode, as well as to decide to select the port in which the communication is happening. And then we have the second part that basically represent the visual interface that represent the messages sent by the DC-DC. So we have all the information we need about voltages, current, temperatures, and also a set of warnings and flags.
Okay. Right now I'm presenting the testing setups and the results that we've obtained. In particular, in this image is reported one of the many setups used to validate the firmware of the system. Here we can distinguish basically three main parts. The most important one is the one indicated at the top right, the blue pill, which is an STM32 development board on which it was loaded the entire DC-DC code. Then a trimmer bank was used in order to emulate the voltages produced by the power board acquisition circuits. And the communication here was managed by an Arduino Uno, which embeds a bridge firmware and an integrated CAN controller. Here is the hardware test performed on the power board. In particular, thanks to the decision of having two different boards, we were able to test all of the subsystems of this board individually. In particular, tested were performed in sequence, one after the other, in order to check the correctness of the behavior of the precharged circuit, the behavior of the enable line, in which we simulated the signal produced by the microcontroller, and the correct behavior of the output stage, in particular the overcurrent shutdown and the current acquisition. Moreover, of course, all of the acquisitions of the voltage and temperature signals were acquired and validated. Unfortunately, during the actual DC-DC test, we intended to perform an open circuit test. We found out that the controller wasn't providing any output. So we started a troubleshooting procedure in order to find the issue, and what we found out was that the controller, in particular the integrated circuit, was not working properly while mounted on the board. So we had two possibilities, which were the wrong design of the board, which has turned out not to be the case because it was perfectly equivalent to the design that we simulated. So we unmounted the device and found out that the component wasn't anymore working. So probably a damage of the stock component, a damage during the assembly procedure. Many things could have happened. Okay.
During all the development of this project, we've analyzed all the possible improvements of this particular device. In particular, we have considered the possibility to build it using high-efficiency MOSFETs and high-efficiency components for the realization. Also design a single board instead of a multi-board structure that could be obviously easier in terms of size. The integration of serial connectors that are safer, more reliable, and offers a stronger connection. And we have considered also the realization of a carbon fiber case, since the one we had was 3D printed in ABS.
Okay. In conclusion, we are extremely satisfied of what we achieved, even if unfortunately we weren't able to provide a fully working prototype. The project was complex, the time was short, it was extremely difficult to follow the deadlines, but we've learned a lot, and we are extremely happy of this experience. It's been a pleasure to work with all of my colleagues, and I hope it's been a pleasure also for them, and thank you very much for your attention. If there are any questions?
I don't think a specific question on this, but then we will have some kind of summary with you.
No, well, first I would like to congratulate to all of you, because I think all three presentations was impressive, so my compliments for the job you have completed. The task was not easy, I tell you, for everybody, so my compliments to all of you.
Thank you. Thank you so much.
All right, and then from my point of view, you achieved what we were expecting. We will go through the documentation as well to check what you uploaded and then see if everything is in place. Guglielmetti from Ferrari, the guy that left beforehand, he said that he would try to, he can offer the possibility for you to have a short video. Quanto aveva detto? Couple of minutes, something like that, to show, if you want to show what happened and for each group, and then they can upload it to the MUNER website and see what happened. And so it could be interesting for you to you know, when you go do the pitching, you go and you present your ideas, they give you a fixed amount of time, very short, and you need to show how much you achieve, what you achieved in a short time. So in a couple of minutes, 2 to 3 minutes max usually, you can show what you did. So if you want to do that, I mean, please do, and then send it to us, and then we can arrange things to show it on the website for the MUNER University. It could be useful, could be interesting for you to add something. From the other point of view, they were trying to think whether to go on a school trip, a gita, in ST Microelectronics maybe, to see where they do and they fabricate all these things. There are 2 possibilities. We will check which one will work better, and we will try to do it before the beginning of next semester, before you start with your internships and stuff like that, so it can be easier to do. What else? In a few days, you will receive you have to fill in your Google Forms. I will collect all your data and arrange it and send it to Claudio. Then we will merge your results with ours and Moreno's in case. And we will, of course, we will have different weights of the results. We will check things and see. Usually you're very good with your colleagues. You always give very high marks to everything. So we need to be more picky and choose all the details. So try to be honest when you do it. I mean, not being, do something that can be constructive for the other. And then at the end, I will send you the final grade. I will upload the final grade on S3, so you will, I will have, I don't know the system in Bologna. The marks will be there. I will send it to you, and you will have a breakout of the details of the marks. Okay. Do you have any other question for this class? If not, so it's been a good experience for me as well. Every year it's better. So we learn how to give. Also from our side, we learn how to do it. Hopefully better for you. I hope you enjoyed it and you learned something. And you will be ready. So I think you will be ready for your first job in some way, because you know how to handle projects, you know how to break down the work, you know how to do your part, you know how to connect with other colleagues, and you know how to handle these complex projects as well. I thank Claudio again for the possibility he gave you to have these intermediate meetings to check how the project was going, so that could help in keeping into the correct track. And I need to have Moreno as well. Where is Moreno? Moreno, thank you very much. Without Moreno, we will be lost completely. So we need to
Absolutely,
thank him
yes.
very much for everything he does all the time with great professionality and a good humor as well. So it's always good to work with him. Thank you, Moreno. Thank you very much. And so it's the end, right, of the semester for you. Good for you. For this class, it's over. No more exams for me, and it's perfect.
Thank you.